So, we are discussing about the second microprocessor operation, which is internal data operations. So, in that we have already discussed about storing of the data, for which we require some registers. Then the second operation is performs the arithmetic and logical operations. So, we require a ALU. The third one is test for the conditions. Okay. Test for the condition, we need some flags, and we have explained the conditions of the various flag to set and reset. Then the fourth operation is sequence the execution of the instructions, for which we require instruction pointer, that also we have discussed in the last class. Then the last fifth operation of this internal data operations is stores the data temporarily during execution. In a defined read write location called stack. Read write location called stack. So, first I will explain the stack, the purpose of the stack pointer and stack in microprocessors. Stack is basically, we know that in 8086 there is a stack segment. So, if I assume that this is the stack segment, this is the starting of the stack segment, this is the ending. Let us assume that this is a 64 kilobytes of the stack segment is there. So, if the starting address is 50000H, ending address will be 5FFFFH, and stack is a last in first out register. Stack is last in first out. So, here the data which is inputted last will be outputted first. So, there is one pointer called stack pointer. So, if the data is filled from here to, suppose here some 32H is there, some 52H, 55H, some FFH, so on up to if the data is full up to here. If this address location is something like 50000005H. So, the next available location for the stack is this. This is next available location. And this is called stack top. The location up to which data is full is called stack top. So, this will be stack top. The location up to which the data is full, and this is next available location. Then the stack pointer is a 16-bit register. So, stack pointer always holds, stack pointer always holds the physical address or the logical address, the offset. Stack pointer always holds the address of the location which is to be executed next. So, always holds the stack top, offset of the stack top. In this case, so the offset will be the first, the distance from here to here. So, this offset is 5005. So, this offset will be held by stack pointer. The contents of stack pointer will be the offset from the starting of the stack segment to the stack top. This is stack segment. So, the stack pointer location will be 5005. Now, what is the need of the stack? This is the concept of what is the need of stack. So, this stack is required. So, whenever you want to execute some subroutines or procedures. So, you might have heard these subroutines in your C programming. Subroutines also called as procedures. That is, if a particular operation repeatedly occurs, like if I want to write the program for the f of x is equal to x square plus 2x plus 3. Here multiplication operation is coming twice, x square can be written as x into x. This is one multiplication whose inputs are, if I write a multiplication program, the inputs are x and x, and this is another multiplication with inputs 2 and x. So, if you want to write two programs, you have to write the multiplication program. Suppose from here to here multiplication program is there. For this multiplication program, the inputs are, you are giving x and x. So, this will give 2x square. Then to perform 2x, again we have to write the same multiplication program, another time multiplication program. This time the inputs we have to give as 2 and x. Suppose if this multiplication program takes 100 bytes say, then to obtain x square plus 2x, requires 200 bytes. This is waste of memory, because the program is same, only the inputs are different. So, instead of writing this multiplication program 2 times, so you write this multiplication program in a subroutine and you call this multiplication program 2 times. That will save the number of memory locations. That is what is called subroutine. So, in any particular program, if a particular operation is repeating several times, so instead of writing that program several times in the main program, you write a subroutine and you call that as many times as you require. So, now what happens is in subroutine concept, this is my main program. So, in the main program what I will do is, this is my main program. I will first initialize these two inputs. I will give the inputs as x and x using some instructions. Then you write a multiplication program somewhere else. This is multiplication program. So, whatever the data that you give, this will multiply and it will feed back the result to the main program. So, this particular multiplication program, this is called subroutine or procedure. So, here we will call the multiplication program. and this is starting address multiplication. So, whenever the call instruction is there, the microprocessor control after this will goes to this one. So, whatever the input that is given before this will multiply those two inputs, and the last instruction of this any subroutine is return. This is RET return. So, here it has to return back to the instruction which is next to this. Then again we will give the inputs. X and 2, again we will call the same multiplication program which is called subroutine. Again here also the microprocessor control will goes to this multiplication program and return back to the instruction which is next to the multiplication program. So, in this way we can save the number of memory locations. So, but here the problem is, so whenever the microprocessor is executing this call instruction, the instruction which is to be executed next is this. So, this will be having some instruction pointer will hold system address. So, suppose if the offset of this particular memory location is some 6000 H, the instruction pointer holds to this 6000 H. Then if I do not save this instruction pointer contents and if I go to this subroutine, while returning, how does the microprocessor knows that it has to return back to this 6000 H? So, that is why what you have to do is this 6000 location has to be stored in some temporary location which is called the stack. So, whenever a call instruction is executed, whenever a subroutine is called in the main program, so what you have to do is before you are going for the subroutine, you have to store the contents of the instruction pointer in a temporary location called stack. So, in order to store this IP contents here in the stack, so if I take this stack pointer in the previous slide, if I want to move this 6000, so we can move these contents into the stack using the operation called push operation. So, if the 6000 contents has been written into this one, so what happens is before this execution of this one, before this contents has been transferred here, these are the contents of the stack pointer. This is 32H, 52H and so on. So, this is 3H, 3FH. Now, contents of the stack pointer will be, this is stack top 55005H. So, once if the call the instruction from the subroutine, so the what will be the inputted here will be the contents of IP is 5000. So, in that the 50 will be first stored in this location which is 55004H, the higher order 8 bits, and then lower order 8 bits will be 00 will be stored here. Then stack pointer contents will be 55003H. Now, what will be the contents of the stack pointer? Now, up to here the stack is full. So, the contents of stack pointer becomes now 5003H. So, before the instruction pointer contents are pushed into the stack, the contents are 50005, whereas after this instruction pointer contents has been pushed, SP becomes this. So, means the SP contents will be decreased by 2, SP becomes SP minus 2. So, this contents of the instruction pointer which will be pushed into this stack pointer or stack memory, this will be internal to the this call instruction. Whenever call instruction is executed, the contents of instruction pointer will be automatically pushed into the stack. So, this in detail I will discuss while discussing about the push and pop instructions of the 8086. So, in addition, not only the contents of the instruction pointer, here the instruction pointer contents has to be saved. This is internal to the call instruction. So, in addition to this, what happens is if I use here all the register for some purpose. So we know that we have the in 8086 AX, BX, CX, DX. So we have different registers. If I use for some purpose, here also you have to write this multiplication program which is subroutine, also using the same registers. So if want to use the same register for some other purpose, so the contents, old contents of this registers will be lost. So in order to avoid that, even all the register contents also you can push into the stack like this instruction pointer, and then you go to the subroutine while return back. So you take all the contents back, which is called pop operation. So in pop operation what happens is, this is the push operation. So in push operation what happens is the contents will be pushed on. This is after push operation, this is push operation. Whereas in case of a return instruction, so the last instruction in the subroutine is return. So inherently in return instruction there is a pop operation. What happens is, in pop, so this in the pop what happens is, this contents will be taken back into the instruction pointer. Instruction pointer contents will become same 5000H. This operation occurs whenever the call instruction is executed. This occurs whenever return instruction is executed. So if I take back this, as I have told, this push is last in first out. The stack operation operates on the last in first out operation principle. So while inputting, first 50 has been inputted and 00 has been inputted. So while outputting, first 00 will be outputted, then 50 will be outputted. So after that again what happens is, the stack type, these two will be empty locations. Now stack top will be points to the previous location 55005. Now stack pointer contents becomes 5005 only. So in the return instruction what happens is, stack pointer will be stack pointer plus 2. So this is about the stack operations. So the need of the stack is, whenever a particular operation is repeatedly coming. So instead of writing that many times the program in the main program, so we can write a simple program in a subroutine and you can call as many times as you require. So in that process we need to store the contents of the instruction pointer and the registers temporarily in some location, memory location, which is called as stack. So while storing, which is called as push operation, the contents of stack pointer will be become stack pointer minus 2, because we are going to save this, and in case of pop operation, stack pointer becomes SP plus 2. So this I will discuss this in detail while discussing about push and pop instruction set of 8086. So this is the fifth operation that will be performed. So these are about the 5 operations that takes place inside the microprocessor, which are called internal data operations. And the third type of the operations are externally or peripherally initiated operations. So what are the operations that will be initiated by the external devices? What are the external devices to the microprocessor? I/O and memory. Okay. So there are some few operations, which is the first operation is reset operation. So reset. So later we are going to discuss about the pin diagram of 8086. In that there is one reset pin. So this reset pin is input to the microprocessor. So whenever the microprocessor receives the reset pin 8086 by external device, this will be connected to an external device. Such as memory or I/O. So any I/O device, external device. So whenever reset is 1, if the microprocessor received a high signal on the reset, so the microprocessor immediately what happens is, microprocessor suspends all the internal operations and sets, resets. So, all the registers like data segment, stack segment, extra segment and all flags to 0. It just suspend all the internal operations and makes data segment, stack segment, extra segment flags to 0. This all these registers will be reset, but code segment will be set to FFFFH. If the reset becomes 0, if the external device releases the reset signal, then what happens is the microprocessor fetches the instruction from which location? So, we know that code segment, the physical address of any location is given by code segment contents into 10H plus instruction pointer. This we have discussed it in the earlier class. This is the physical address. So, now when the reset is 1, what are the contents of the code segment? Is FFFF into 10H. What will the contents of instruction pointer? Even instruction pointer also here set to 0 plus instruction pointer is 0000H. Therefore, the instruction becomes F 0 plus 0000H. This will be FF0H. So, the microprocessor fetches the instruction from this address location. This is about the reset operation. So, whenever the microprocessor receives a reset signal from the external device, it suspends all the internal operations and sets data segment, stack segment, extra segment, instruction pointer and flags to 0, whereas code segment will be set to FFFFH. So, if the reset becomes 0, the microprocessor then fetches the instruction from the physical address, which can be calculated by using code segment into 10H plus instruction pointer, which becomes FFFF0H. This is the first externally peripheral or peripherally initiated operation. And the second externally or peripherally initiated operation is ready. So, the microprocessor is having another signal called ready signal. So, any peripheral will be connected to the microprocessor through ready signal. Peripheral device, if it is connected to ready signal, so if ready signal is 0, microprocessor receives a low on ready signal. So, microprocessor will enter into the wait state. So, this is something like if the microprocessor want to take the data from a peripheral device. Normally, the peripheral device is slow when compared with the 8086. So, because of this, the first microprocessor will initiate for the data through some request, data request. So, if the peripheral is ready to give the data, it will send high on the ready signal. So, till the data is ready, because the peripheral is slower when compared with the microprocessor. So, this will make ready is equal to 0. So, microprocessor simply waits in the wait state. So, if the ready is 1, microprocessor read the data from the peripheral through data bus. So, basically this ready operation will be used to synchronize this lower peripheral with microprocessor. Basically, ready signal will be used for synchronizing this lower peripheral with microprocessor. This is the second externally or peripherally initiated operation. The third one is interrupt. Interrupt. So, whenever the microprocessor receives the interrupt, so this is the main program in the microprocessor 8086. So, interrupt can be of two types. It can be software interrupt or hardware interrupt. In any case, the operation is same. The interrupt can be hardware or software. Software interrupt, as the name implies, there are some instructions which will act as interrupt. Hardware, there will be pin corresponding to each hardware interrupt. So, depends upon the position of that particular pin, whether you have to make high or low to high transition, high to low transition. So, accordingly the microprocessor will be interrupted. Suppose if the microprocessor is executing the programs one by one. So, while the microprocessor is executing this program, this instruction, let us assume that if the starting of this one is some 60,000 H and if the address of this one is 6500 H. So, while the microprocessor is executing this instruction, so what will be the contents of the instruction pointer? As I have discussed in the earlier class, the instruction pointer always holds the offset from the starting of the segment. So, what is the offset here is 5000. So, this 5000 will be held by the instruction pointer. Instruction pointer holds the offset from the starting of the segment. So, the microprocessor is supposed to be execute this instruction after this instruction, but while executing this instruction, the microprocessor has received the interrupt. Let us assume that while the microprocessor is executing this instruction, microprocessor has received the interrupt. So, what the microprocessor will do is, first it will execute the current instruction. After that, so instead of going for the next instruction, the microprocessor control will goes to, after the execution of this instruction, there is one subroutine called interrupt service subroutine, interrupt service subroutine, which is similar to the subroutine which I have just discussed for the call instructions. Where you can write some program. So, normally this interrupt will be activated whenever you want to perform some emergency task. The microprocessor is executing some program. So, whenever you want to perform some emergency task, you interrupt the microprocessor, you disturb that current running of the program, then you go to this interrupt service subroutine, you write the instructions here to perform the emergency task. Then the last instruction of this one is similar to any subroutine, return. So, while it is going for this interrupt service subroutine, this instruction pointer contents has to be saved into the stack, as you have discussed just now. Then in the return, what happens is the contents of the instruction pointer which are stored in the stack will be again taken back into the instruction pointer. So, the control will automatically goes to the instruction which is next to this interrupt, next to the instruction which is next to the interrupt. So, you see the process, this is exactly similar to this call and return instructions. So, after execution of this instruction, this will goes to subroutine. So, you see how the interrupt will occurs. Okay. So, in 8086 there are many software interrupts that I will discuss. There are two hardware interrupts in 8086. In 8086 there are two hardware interrupts. They are called INTR and NMI. NMI stands for non-maskable interrupt. So, this is where this one is interrupt, just simply this is maskable interrupt. So, what is meant by non-maskable and maskable? So, this non-maskable, as the name implies, it cannot be disabled. This can be used to interrupt the microprocessor at any time, whereas INTR can be disabled by the programmer. Suppose the microprocessor is executing the main program itself, some emergency task in the main program itself, that time it can disable this INTR through some program, but NMI cannot be disabled. Even if you want to execute some emergency program here, the NMI can be used to interrupt the microprocessor, and it can be asked, it can be forced the microprocessor to execute some other which is interrupt service subroutine. So, it is the difference between maskable and unmaskable. Maskable means which can be disabled, so NMI means which is not disabled. But when does this INTR will be enabled, NMI will be enabled. So, this INTR is called positive level triggered interrupt. INTR is a positive level triggered. So, if I want to interrupt the microprocessor through INTR, so if I take the clock signal, we will be having totally 4 divisions. This is called positive level. The means a duration for which this clock is equal to 1, clock is equal to 1, logic 1 is called positive level. And this is called where the clock is equal to 0 is called negative level. The transition from 0 to 1 is called positive edge or leading edge, transition from 0 to 1. Is called positive edge or leading edge. Whereas the transition from 1 to 0, transition from, sorry, not this. So, this is transition from one to 0 is called negative edge or falling edge, or even it is also called trailing edge. So, when does the microprocessor interrupt will be enabled? So, if we take this INTR during this portion only. So, whenever you give this INTR line, this is INTR line, this is INTR line. If I apply this 5 volts to this one, that is called positive, which is logic 1, then only this INTR will be enabled. Whereas NMI, non-maskable interrupt, is positive edge triggered interrupt. That is, if you want to enable this NMI, you have to give a transition from 0 to 1. So, if this is NMI signal, if this is my ground, this is my 5 volts line, then you take this NMI signal, first you connect to 0, then you connect to 5 volts, then only this NMI will be enabled, 0 to 1 transition, which is called as positive edge. Whereas INTR is positive level. If I make simply plus 5 volts here, INTR will be enabled. So, these two are these hardware interrupts INTR and NMI in 8086. So, INTR will be a positive level triggered, NMI will be positive edge triggered. This is one difference. So, another difference is INTR can be maskable, NMI cannot be maskable. So, this is how the interrupt, whenever the microprocessor want to execute some emergency program by the external device request, so it will execute that program through the interrupt. The fourth external operation will be hold operation. So, we know that the microprocessor block diagram of this microcontroller is, we can have the microprocessor, memory, IO. These two are bidirectional. This is a simplified block diagram of any microcomputer. As I have told, microprocessor is useless unless otherwise it is connected to memory and IO. So, because the microprocessor is having address and data buses, so if the memory want to transfer the data to the IO, so the regular process will be, so first memory will transfer the data to microprocessor, then from microprocessor data will goes to IO. Because why this microprocessor is having address and data buses? For address means data transfer, address and data buses are required. So, for that is why the memory will first place the data into microprocessor, then from microprocessor the data will goes to the IO. This is a time consuming process. For small data transfers we can use this process. If the data to be transferred is huge, so in that case this is time consuming process. So, instead of that, if I directly transfer the data from memory to IO or IO to memory, this is called direct memory access, DMA. So, we can do this direct memory access to save this time. So, we can transfer the data directly from memory to IO. But what is required here is, if I want to transfer the data from memory to IO, so I have to take the control of the buses from the microprocessor. So, for that the peripheral device, memory or IO, even IO can be transfer the data to the memory directly. This is a bidirectional. So, these two peripheral device, any peripheral device. So, if any peripheral device want to make DMA data transfer, this is microprocessor, any peripheral, this can be either memory or IO. So, first it has to take the control of the address and data bus of the microprocessor. Further the peripheral will request the microprocessor through a signal called hold signal. So, hold signal is a request for the microprocessor to hand over the control of address and data buses to the peripheral for a DMA data transfer. So, whenever the microprocessor is ready to give this address and data buses, so it will acknowledge through hold acknowledge signal, HLDA. This is hold and this is hold acknowledge, HLDA. So, once if the peripheral receives the hold acknowledge, after that the control of the address and data buses will be given to the peripheral, then the peripheral, it can be memory or IO, it will directly transfer the data to the other peripheral. So, after the data transfer is over, again the control of the address and data buses will be given to the microprocessor. This is what is called direct memory access. So, we will discuss this DMA also. There is one IC, exclusive IC for direct memory access, DMA. So, we will discuss more details that time. So, this is the direct memory access. So, in this we will use hold and hold acknowledge signals. This is also externally initiated signal. So, these are all this the microprocessor operations. Till now we have discussed about. So, all the three types of the microprocessor operations. The first one is the microprocessor initiated operations such as memory read, memory write, IO read, IO write. Second one is internal data operations. So, like storing of the data, performing arithmetic logical operations, then checking for testing for the conditions, sequence the execution of the instructions, stores the data temporarily during the execution in a memory location called stack, Then there are some externally or peripherally initiated operations, so which are reset, ready, interrupt and hold. Okay. So and the corresponding the hardware elements and the signals that are required for the 8086 we have discussed. So with this discussion, now we can move to the architectural diagram of 8086, and then we can discuss about the different pins of 8086. This is all the brief introduction to the 8086. Now coming for this 8086 architecture. So this is internal architecture of Intel 8086 microprocessor, so which is taken from the Intel Corporation. So these are the different blocks in 8086. So basically this entire architecture is divided into two parts. One is called bus interface unit, BIU. This is the BIU, this above one dotted one. This one is called BIU, and this one is execute unit, EU. So what is the purpose of BIU? What is the purpose of EU? So BIU actually it will send the address to the external device. To the memory, because where the programs will be stored in the memory. Okay. In order to execute that instructions or the programs, so this microprocessor has to fetch the instructions and then it has to be executed. So for that BIU, bus interface unit, BIU stands for bus interface unit, send the address to the memory. So this is the memory outside, memory interface, and we can have IO also. So we have memory interface, we can connect to the IO device also. Here this connection can have, this can be connected to IO also. So BIU sends for the address to the memory location. So from that particular memory location it will fetch the instructions one by one, reads the instructions, from the memory location, then in order to execute the instruction it may require the data also, reads the data, so this reading of data can be either from the memory or IO also. So reads the data, then execution will not be takes place here, execution as the name implies, execution will takes place here. So after the execution again the results will be sent back to the either memory or IO. These are the various operations in bus interface unit. It sends the address, so that in that particular address we will be having some instruction, that instruction will be fetched into the BIU, then whatever the data that is required to execute that instruction it will fetches from the memory or it can be from IO. So after that, that data will be given to execute unit, execute unit will execute, after that the results will be sent back to BIU. So the BIU basically sends the data results to the either memory or IO. So basically this BIU is going to interact with the outside the world, and as the name implies execute unit, so it decodes the instructions, decodes and execute the instructions. So here one important thing here is, here in this bus interface unit there is a 6 byte long instruction queue. So what happens is microprocessor will fetches the instructions. So if the microprocessor fetches the first instruction, after fetching the first instruction from memory it fetches the instruction, this will send this instruction to the execute unit for decoding and execution. So while the microprocessor is executing the first instruction, so this bus interface unit fetches several instructions up to 6 bytes, 6 instruction bytes. It prefetches and stores in a temporary location called queue. So this queue is first in first out register set. So each one register, total we have 6 registers, So, this Q is first in first out register set. So, while the microprocessor is executing, execute unit is executing the first instructions. So, it will fetch the 6 instruction because this will take the time. So, during that time the microprocessor means the bus interface will not be ideal. So, what it will do is it will fetch the 6 instructions, as many as 6 instruction bytes, and it will store into the queue. So, what is the advantage of prefetching the 6 instruction bytes while the first instruction is being executed by the execute unit? So, in this way what you can do is we can overlap the fetching operation with execute operation. So, this is what is called pipelining. So, 8086 is operates in pipelining mode. This pipelining is nothing but overlapping of fetch and execute cycles. Is called pipelining. So, what is the advantage of the pipelining? Because we are going to overlap the fetch cycle and execute cycle, you can speed up the operation. Thereby we can speed up the operation. This is the advantage of this 6 byte instruction queue. So, while the microprocessor is executing the first instruction, we can store 6 bytes here. So, now the microprocessor will take the instruction from instruction queue. So, this instruction will be fetched into the instruction queue. If this instruction is having a space for at least 2 bytes, then only this BIU will fetch the instructions from the memory. So, from the memory the instructions go to instruction queue, from instruction queue it will go to the execute unit, then after execution again results will be sent back to the either memory or IO device. And the remaining blocks, most of the things we have already discussed. So, we have this segment registers, extra segment, code segment, stack segment, data segment, instruction point. The purpose of all these registers we have already discussed. And this is arithmetic logic unit. This is actually this physical address calculation unit. As I have told how to compute the physical address from the offset or the logical address. So, this particular code segment or any segment contains the contents of the segment register into 10H plus the contents of instruction pointer or any base pointer. So, in that way you can compute physical address. This is 20-bit physical address, this is 20-bit physical address, this is 20-bit physical address. Whereas these registers are 16-bit registers. So, to obtain this 20-bit physical address from 16-bit registers, we can use this operation, the operation that I have already explained. So, the contents of any segment register plus 10H into instruction pointer or any base pointer or index pointer, depends upon the type of segment that we are going to use. So, it is about this bus interface unit blocks, and then coming for this execute blocks, execute unit. So, we have different registers as I have told, AH, AL. This can be used as AX as a whole, this can be used as BX as a whole. 16-bit, if you want to store the 16-bit data, we can use BH and BL as BX, CH and CL as CX, DX. If want for 16-bit operations, we will use AX, BX, CX, DX. For 8-bit operations, we can use AH, AL, BH, BL, CH, CL, DH, DL. And then we have stack pointer. Just now I have explained the stack pointer operation. Stack pointer always holds the offset from the stack, means start of the stack segment to the stack top. And base pointer will be basically used in calculation of the physical addresses for data segment and extra segments and all. Similarly, we have source index and destination index. These will be useful in string operations, which I have discussed in the last class. So, these are all about the register array. Then arithmetic logic unit, which performs all arithmetic and logical operation. The size of arithmetic logic unit is here 16-bit, because this is 16-bit microprocessor. So, the size of the ALU is going to decide how many bit microprocessor is that. Then we have some flags which I have already explained. So, now to compute all this operation, we require some control system. This is about the internal architecture. So, most of the blocks we have already discussed while discussing about the various microprocessor operations. And then coming for pin diagram. So, totally there are 40 pins, 8086 is a 40 pin IC. So, these are the 40 pins. There are some common signals, there are some specialized signals. So, this from here to here, the microprocessor can operate in two modes. One is called minimum mode and maximum mode. Minimum mode is single user and maximum mode is multiple user. So, multiple users can access the 8086 at the same time, which is called multiprocessing. So, in that case we have to operate this 8086 in maximum mode, for single user in minimum mode. So, in any case except these 8 signals, the remaining signals are common whether it is a minimum mode or a maximum mode. So, these signals, this set of signals are for only maximum mode, whereas this set of signals are minimum mode signals. So, we will discuss the functions of each pins. So, in the next class, first I will discuss about the minimum mode signals. So, maximum mode signals we will discuss later. So, the functions of each pin, most of the signals we have already discussed like NMI, INTR, this reset, hold acknowledge. Okay. So, whichever the signal that we have missed we will discuss in the next class. After that we will go for the instructions of 8086. Thank you.